So if you recall, previously we talked about what a condition variable was and what pattern it implements, which is the guarded suspension pattern. I talked about how condition variables are often applied in practice, and they're used in conjunction with mutexes or locks of some kind in order to make sure that the condition that's checked is properly synchronized to avoid race conditions. And then I gave you a somewhat whimsical example of a human known use of condition variables where we were trying to deliver pizza, and we needed to have keys and a pizza in order to do that. What we're going to do now that we've kind of given the background is we're going to talk about Java condition objects, and I'll explain how Java condition objects allow concurrent programs to have multiple weight sets per user-defined object. So an object in this case is just a Java object, and we'll see that out of the box, if you use the built-in condition variable that's part of the monitor object that every object in Java is, that you have limitations. You can only have one weight set per object. When you use condition objects, you can have multiple weight sets, and I'll explain why that's significant. Okay, so what is a condition object? Condition object is basically the class in Java that provides the realization of the condition variable abstraction that we talked about. So you can see Java condition object is a class. Java condition object implements the condition interface. And if you read the interface description for condition, it talks about what these things are. It's always worth reading the documentation. As you get more comfortable with it, it'll make more sense. And internally, the condition object is actually, from an implementation, deployment, or not deployment, from a physical implementation perspective, condition object is actually nested within the abstract queued synchronizer class, which is kind of a weird place for it to be, but that's where it is. And remember, the abstract queued synchronizer class defines a framework that's used by a bunch of Java synchronizers, such as reentrant lock and semaphore and condition object, in order to be able to use so-called FIFO wait queues that wait in, first out order. So you can see here we have abstract queued synchronizer. It's got nested inside of it a condition object, and condition objects are made up of 0 or more nodes, and we'll see how that gets used in a second. Internally, the condition object basically provides a wait queue of nodes. So these are the nodes that are used to essentially have threads wait to get a chance to try something again. That's kind of the idea. And if you take a look at the link at the bottom of this slide, there's a nice paper written by Doug Lee explaining the abstract queued synchronizer framework. It's worth taking a look at for a deeper understanding of what's going on. So the thing to remember when you think about a condition object, it's used to be able to provide a wait queue of nodes that are used to allow threads to wait for conditions to occur. So the threads, which are basically the wait set, a lot of kind of unusual terminology. You have these threads, which are the wait set. They use the condition object in order to coordinate their interactions by selecting the order and conditions under which the threads will run. So that's kind of what it's described in an abstract sense. I will then, of course, give you lots of examples and talk about more how it works under the hood. So you recall when we talked about condition variables, which is the concept, I mentioned how condition variables were always used in conjunction with some kind of mutex or lock. And now that we're seeing condition objects, which are the Java realization of the abstraction of a condition variable, we'll get a chance to understand this in a little bit more detail. So a condition object is always used in conjunction with a lock or something that implements the lock interface. And often a reentrant lock, although you can use other stuff as well, but that's the most common thing to do. So if you use a condition object or 2 or 3 or 4, there'll always be some kind of lock that's associated with that condition object. And the purpose of this lock is to protect the shared state in the condition expression that you're using to decide if you get to go within the guarded, the guarded suspension guard, in order to be able to ensure that that thing is not going to incur race conditions when it's accessed or updated concurrently. So we need the lock to protect the condition expression from concurrent access. And I'll explain this in the in an abstract sense first, and then I'll show you lots of examples that make this more clear. By the way, does anybody know what that picture is? Yes, and what's happening? That's exactly. Joe gets 10 points, right? So you get A+. So yeah, that's Eowyn is guarding the king from the Witch King. So that's the guarded protection. There's a factory method here called new condition. And Rantrant Lock has a factory method called new condition. And you remember a factory method is something that's used to make something. And this returns a condition object that can be used in conjunction with this lock. So that's where you're going to get a condition object from. So you typically don't say, new condition object. You say Rantrant Lock dot new condition, and that goes ahead and makes it. Amanda. So remember how we talked before? The question is, how does a condition object differ from a condition variable? Remember we talked before about the concept of a mutex or a recursive mutex. We talked about this concept, and then I said Rantrant Lock is the way that Java, one way that Java implements a mutex. There is also stamped lock as another way. It doesn't happen to be recursive, but they're both examples of mutexes. So in the same way as Rantrant Lock is a realization of the concept, the abstract concept of a mutex, mutual exclusion lock, so too is condition object the realization of the condition variable abstraction. So you can imagine a world where there would be other ways to implement condition variable besides condition object. But condition variable is the concept, condition object is the realization or the instantiation or the reification, right? It's taking the concept that's abstract and making it something you can program to. And you'll see, by the way, that there are other realizations of condition variables in Java, such as the Java built-in monitor objects. Every Java object is a monitor object. And it also has a realization of the condition variable, just has some limitations and some strings attached, which we'll talk about. But yeah, that's a good question. So Rantrant Lock has a new condition method that makes a condition object. And by the way it works is it returns something of type condition, which is the interface, but the implementation under the hood will be condition object. Both Rantrant Lock, or both an instance of a Rantrant Lock and an instance of a condition object, have internal queues. And these queues are used for slightly different things. The queue for the Rantrant Lock is used to queue up threads that are waiting to acquire the lock. So remember, as we talked about before, think about the queue of waiters at a restroom in an airplane where they're queuing up to get into the restroom. So that's kind of the Rantrant Lock queue. Likewise, condition objects also have a queue, and that's a queue of threads that are waiting for some condition to potentially become true. So in this case, that's kind of like the example I gave you, for the pizza delivery example or use case where you have a queue of pizza delivery people waiting to get a pizza and get the keys to the truck so they can deliver the pizza. So again, different queues, but they both have queues. The queues are implemented somewhat differently, but they do more or less the same sort of thing. A user-defined Java object, in other words, something you implement as a user, can have multiple condition objects, or COs. So, for example, our ArrayBlockingQueue implementation has got two condition objects, not empty and not full. And we'll talk a little bit later about why we have two of them. But in the long and the short of it is that we have two of them in order to be able to have distinct wait sets for different conditions, waiting for the queue to be empty on one hand and waiting for the queue to be full on the other. And this turns out to be one of the benefits of using condition objects is you can have multiple of them per user-defined object. And this is good because it allows us to be able to do more sophisticated and more efficient ways to coordinate the interactions of multiple threads versus something else we'll talk about in a second. So the way this usually works is you'll end up having multiple condition objects that share a common lock. And these condition objects will be notified under different conditions, as the idea implies here. If you're trying to take something from the queue and the queue is empty, then you're going to wait on the not empty condition till there's something in the queue. Conversely, if you're a thread or threads that are trying to put something in the queue and the queue is full, you'll wait on the not full condition until the queue becomes not full. So that's why we have two conditions. And I'll talk more about that in a second. You'll see why it's a win to have two of them. In contrast, the other way to be able to realize, or another way to be able to realize the condition variable abstraction in Java is to use Java's built-in monitor objects. Remember, everything by default is a monitor object. And every object is a monitor object. Int is not a monitor object, but everything else is. And in that case, every monitor object has one and only one wait queue, because they have what's called an implicit, the intrinsic condition object, and using the word, I should probably say the intrinsic condition variable. And so basically the monitor has one of these things. So there's only one wait queue. And that ends up being a real hassle for a variety of reasons, because it means that you typically end up having to use the notify all method as opposed to the notify method, for reasons that will become a little clearer later on. And what happens here is that because there's only one wait queue, waiters end up having to use the same queue to wait for different types of conditions, which turns out to be really inefficient and weird. So for example, if you implement the simple blocking queue, which is one of the implementations that lurks in my GitHub repository, you'll see that whenever it puts or takes something into the list, into the queue, it calls notify all, which wakes everybody up, even though you don't really have to wake up one half of the waiters because they're not waiting for what you just did, right? So in this case, if we do a take, we're going to notice that there is, the queue is no longer empty, and so we call notify all. Well, we don't really need to call notify all conceptually, because we just want to be able to wake people up who were waiting for the queue to no longer be full, because we just took something out of it. But because of the way that there's only one wait queue with Java built-in monitor objects, we have to call notify all. And that's inefficient and bizarre. So the good news is, by using condition objects instead of using the one and only intrinsic condition variable, what's sometimes called the monitor condition in a built-in monitor object, we get a lot more flexibility. And this will become clear a little bit later. So let's talk first about some of the key methods of Java ConditionObject. These key methods basically allow threads to wait and notify on each other, so they can coordinate their interactions. That's what these methods do. They're used to coordinate stuff. Interestingly enough, the method names are actually quite similar to the methods that are defined in Java Object. Remember, Java Object has wait, notify, notify all. Those are the methods that every Java object gets, every object in Java gets by virtue of the fact that it implicitly inherits from Java lang object. And for various reasons, Java lang object has final methods. Notify, notify all, wait, those are final methods. So we can't actually override them. So instead, we have to define new methods, await, signal, and signal all. So you see they're very similar, right? It's await instead of wait. It's signal instead of notify. It's signal all instead of notify all. Do not mix and match these things. Do not have a condition object that calls wait. Don't never call wait on a condition object. Chaos and insanity will break out because it's mixing and matching the different mechanisms. It's sad that they couldn't quite handle this. This is clearly a case where the original design of Java wasn't anticipating the use of condition objects, and so when they added it, it was kind of a shoehorn, and you just have to be very, very careful with how you use it. Internally, these methods are implemented using the abstract queued synchronizer framework, which we talked about before, and it's really quite fascinating. If we have some time at the end of the class, I might walk through the code and show it to you. It's really interesting. What does await do? Await basically suspends the calling thread until some other thread signals it. So basically what it does is it takes the calling thread and it parks the calling thread on the queue on this condition object. And if you take a look, there's a method actually called park, which is used to put something on the queue. So it's basically going to add it to the end of the queue. Signal is going to move the longest waiting thread. So here's the thread that's been waiting the longest, right? The person in the front. And it's going to move that thread from the condition object to the queue for the owning lock. So what that implies is that by doing this, it's not going to have that thread start to run right away. That thread gets to simply go stand in another line and wait for its chance to get in there and acquire that lock, and then it can run. So signal is just about moving things from one queue to the other, and that makes sure it'll get to a point where it can actually do something. Think of it, I'm trying to think of a good example of something like this. Let's see. If you go to the airport, oftentimes, oh, I know it. If you go to a supermarket or a store where you have lots of checkout counters, there'll often be sort of one line that everybody stands in, and then when you get to a certain point, they'll say, okay, you go stand in that line over there. Actually, probably the best example of that would be when you go through like international airport security, where they're moving you from queue to queue. So you get moved from one queue to a queue where you're actually going to get handled in the near future. So that's what signal does. It moves the longest waiting thread from the condition object's wait set into the queue for the owning lock. Signal all moves all the threads from the condition object's queue to the owning lock's queue, right? So they're all now ready to run. And we'll see in a second that leads to something called the thundering herd problem. And you can really sort of get a sense of why there is a thundering herd problem. Let's say you have lots of threads that are blocked on a condition object, waiting for something, waiting for a message to come in, or waiting for the queue to be not empty or not full or whatnot. And when you call signal all, it's going to move them all over to the owning lock's queue, and now they're all going to get a chance to run. And that, as the name implies, could end up creating a very large amount of overhead, because it's a thundering herd. So if you want to read about the thundering herd problem, you can read about the thundering herd problem. But basically, the point is using signal all is a very, very inefficient way of doing things. And that's why the built-in monitor condition that you get with built-in Java monitor objects is inadequate and inefficient, because you have to use notify all most of the time, which just exacerbates the thundering herd problem issue. There are some other methods in condition object. Most of them are variants of a wait. And you can see here that we have ways of being able to wait for a certain amount of time. You can wait in a very fine-grained way with nanosecond timeouts. These are up to millisecond resolution. This is nanosecond resolution. You can wait uninterruptibly, which says don't interrupt me while I wait. And you can also await until some deadline, which is a little bit different, because you say, don't wake me up until this time expires, whereas these say, put me to sleep for this up to this amount of time. Sort of variants of the same concept, but slightly different. And you could take a look at this link to find out some discussions about waiting for things. One of the other big downsides with built-in condition objects, not the ones we're talking about here, but the monitor conditions that are built into Java built-in monitor objects, is there's no easy way of being able to figure out why something returned from a call to wait if it's timed. You don't know whether it's because the timeout elapsed or the thing was notified. Really major glitch. So luckily this is fixed in Java 5, because await will return whether or not it was interrupted or not, which is useful to know. Okay, so that's the end of part 3 of discussion of condition object. So now that you have a better idea of what the condition objects do in terms of a class, what the methods are, and some vague ideas about how you await and signal all, let's go ahead and take a look at how you can actually use this stuff to write real Java code. And as before, we'll take a look at the implementation of the array blocking queue. So array blocking queue, as I mentioned before when we talked about reentrant lock, is essentially a blocking bounded FIFO queue. The array blocking queue extends the abstract queue superclass, so it gets some implementations from that. It then also implements the blocking queue interface, which gives methods like take and put with certain semantics that are assumed by those methods. And we'll look at both the interface and implementation of this to see how condition objects are actually used in practice. Internally, this is again just to recap what we talked about last time. The array blocking queue is implemented by a dynamically sized array. And this is the state. These are the fields that need to be protected from race conditions. And also, we want to be able to coordinate concurrent put and take calls. And so we have array of items. We have a take index and a put index. That just keeps track of where you put and take things into the array of items. And then we've also got some other stuff. These are the actual synchronizers that are used as part of the array blocking queue implementation. So we have a reentrant lock. That's what we looked at last time. That's obviously used to protect the state, to ensure we get atomicity, ensure visibility constraints, ensure ordering constraints are all obeyed properly. And then we've got a pair of condition objects that are accessed via their condition interface. And these are not empty and not full. And you'll see why we need both of them in just a second. OK, so we talked about reentrant lock earlier. The two condition objects, the reason we have two condition objects is in order to be able to solve this limitation with Java built-in monitor conditions, where there's only one. So by having two, we'll be able to separate the weight sets for consumers, which are trying to take stuff from the queue, and producers who are trying to put stuff in the queue. And the nice part about that is that'll make things much more efficient, and we'll avoid having to wake everybody up. We get rid of the thundering herd problem that we talked about before. That's a problem with the built-in monitor objects that you get with Java, because there's only one condition as opposed to the ability to have multiple conditions. Here's the constructor. We're going to take in a capacity, which is used to make the size of our bounded buffer. So we have a bounded amount of objects here of size capacity. We then go ahead and make ourselves a new reentrant lock with whatever the parameter that's passed in, be it fair or non-fair. If you recall, fair meant it FIFO queues them. Non-fair means anything goes. Whoever gets there first gets the next item. And then using that lock, we're going to call its new condition factory method twice in order to be able to get two condition objects, not empty and not full. And so you can see that both those condition objects, not empty and not full, are going to share a single lock. So we have two condition objects, but they both are associated with the same lock. And that's very, very common. The reason we do that, of course, is because the state that's involved here is going to be shared by both people who are putting things into the queue and taking things out of the queue. So we want to make sure that they're protected by the same lock. If we have two separate locks, then we were trying to share state, we'd have all kinds of race condition problems again. Let's kind of visualize how this stuff actually works. And so this will visualize how it works, and it'll also show you sort of the various bits and pieces of the implementation as we go through this. So this is going to implement what's called the monitor object pattern, which you can read about at the link at the bottom here. And the purpose of this pattern is to synchronize method execution to ensure that there's only one method at a time that's able to run in an object. Another way of putting that is only one thread can call a method defined on the object and run at a time in the critical section. And we can also allow the methods to cooperatively schedule their execution, right? So you have to do take, but if you do a take, you can't actually run until someone does a put, right? So you can coordinate the order in which things actually run. And we'll see this using a little diagram here. This diagram is a diagram that illustrates the monitor object. And as you can see, it's going to have a critical section, which is where the code execution will take place. It has this little anteroom that's like a lock that's used to sort of, defer access, so there's only one thing in here at a time. And then we've got these two things off to the side called not full and not empty. And those are essentially queues where threads wait when they aren't able to make forward progress. And I'll explain how that works in a second. So many of the steps we're about to look at apply for both the monitor object pattern and also the Java condition objects. So a lot of this stuff is very similar. You'll see the main difference comes with notify versus notify all. So let's take a look at how a condition object could be used for one thread, thread T1, to attempt to take a message out of an array blocking queue that has nothing in it. So we'll have a queue of 10 items that has not got anything in it yet. So 10 is the capacity, see up here. And some thread T1 comes along and says, I would like to get an object, or I'd like to get a message out of that queue. Let's say it's a queue of strings, for the sake of argument. Here's what take does. So since there are no other threads at the moment, let's assume, thread T1 will be able to come in and acquire the lock. And since there's no contention, it'll come right in. And that will allow it then to enter the critical section, since there's no contention from other threads. It's then able to run. And let's say, for sake of argument, that it's going to check the guard on the guarded suspension portion of our implementation. So this is the guarded suspension pattern. And it's going to say, while the count is 0, in other words, while there are no messages in this queue, then go ahead and wait. And you can see it's running inside the critical section, doing that check. And then when it discovers that it can't make forward progress because there are no messages, it goes and it parks itself in this little ante-room, right? This little waiting room, let's call it. And it's the not empty waiting room. So the thread comes into the not empty waiting room, and that, as you recall, will atomically block the thread and release the lock. So the lock is now available for somebody else to use if they want it. Let's assume now that we're blocked, that the thread 1 is blocked waiting for something to show up. And let's assume, to make the example interesting, that another thread, thread T2, comes along and it wants to put something in the queue, right? So think about producer-consumer interactions, right? The consumer's blocked. We now have a producer that comes along. So the producer is going to call put on the queue, and that is going to, and the queue is currently empty, and it's got thread T1 that's waiting off to the side on the not empty condition object. So what happens, T1 comes in, and it's going to go ahead and acquire the lock, and that will allow it to get into the critical section, because at the moment, let's assume there's no other contention. And once that happens, then it checks the guard. This is the other guard, right? This is the guard to see if the queue is full. The other guard the first guard we looked at, checked to see if the queue is empty. Now we're checking to see if the queue is full. And what this will do is it's going to block until the queue is not full. Well, at this point, the queue is definitely not full because it had 10 items and there's 0 in it at the moment. So this is going to succeed, and we're going to skip the await call because we don't ever have to worry about that case at this point because there's nothing in the queue yet. At that point, with the lock held, the insert method is called to insert the element into the queue. And you can see that this is all taking place. T2 is running in the critical section. T1 is still blocked. Insert is not synchronized because it assumes it's called with the lock held. And that's something that's called thread-safe interface pattern. We then go ahead and stick the item in the next index in the queue, increment the index by 1, wrapping it around if necessary because it's a circular queue, incrementing the count of elements. All those things are done atomically because the lock is held. And then the last thing we do before we leave insert is we signal the not empty condition saying, anybody who is waiting for this queue to be not empty, you might want to check it again. You might want to wake up and check it because I just put something in the queue. So that's basically informing any waiters that are waiting for that condition that they might get a chance to run again. The last thing that happens on the way out here is we're going to go ahead and release the lock, and that will allow us to leave the monitor. So we're no longer in the monitor. The monitor lock is now available for use. And also, by the way, we've notified the not empty condition. So you'll see in a second what's going to happen here. All right, so let's assume that that's just happened. And what's going to happen here is that thread T1, which was asleep in not empty.await, when thread T2 calls signal on the not empty condition, that will cause await that'll cause the thread to wake up in the context of await. And it'll say, aha, I am now able to move from the waiting set of the not empty condition object to the queue of threads, if there are any other threads, that are waiting to get into this lock. And the lock is, of course, the lock up here, the lock that's protecting the overall monitor. And so what will happen, of course, is, let's assume for sake of argument, there are no other threads at the moment. So this thread will wake up, be put on the queue, and then go and check to see that there's nothing else there. So it'll go ahead and scoot right in. It'll grab the lock, lock it, and all that happens before await returns. So await will not return until it's got the lock. And then with the lock held, it loops back around again, and it checks to see whether or not the count is still 0. Now, we saw that the count was incremented by 1 by thread T2. So why would it not always be the case that this thing wouldn't just succeed? Why do we have to loop back around again and check? And the reason is there could have been another thread that was ahead of us in line, and so when the condition was notified, that other thread might have gotten awakened first. And so as a result, we always have to do this check in a loop. So we do the check. We discover, for sake of argument, that count is no longer 0 because there's at least one item in the queue. So that succeeds. And then we go ahead and call extract with the lock still held. And the extract method, as you can see here, goes ahead and essentially takes the next item out of the queue, futzes around with the take index to increment it by 1, wrapping it if necessary, decrements the count. And then the last thing it does is it signals the not full condition, saying, hey, if anybody was waiting for this queue not to be full, I just took something out of it. So you might want to wake up and see if you can put something into it. And then it goes ahead and returns the item that was extracted. That item will be returned by the take method, but in the finally block, we unlock the lock. That allows the thread to leave the monitor, and then allows the monitor to be accessed. The monitor lock is now available, so someone else can come along and try to do a put or take. This example is not trivial, and it's funny. You can look at it from 17 different ways. This is sort of a combination of code and visualization. You can just do a pure visualization view. It's subtle and it's tricky, and the reason it's subtle and tricky is because there are multiple moving parts, right? There's locks, there's multiple condition objects, there's code, there's a critical section. And so not a bad idea if you're still having a hard time putting the pieces together to go back and rewatch this video and then think about this in the context of your assignment 2B, because you're going to have to implement a semaphore using the various pieces that we've been describing here. OK, so that's the end of part 4. So the last part of the lesson on condition objects is going to focus on kind of use cases and usage considerations. How should you use this stuff effectively? So condition object is highly flexible. I am not that flexible, but that doesn't mean I can't appear to be that flexible through the magic of Photoshop. So it's very flexible. And the reason it's flexible is because it allows threads to suspend and resume their execution based on shared state, which is what are used in the condition expressions in order to check things. So for example, we can have threads T1 and T2 take turns sharing a critical section. So in this example, T2 is blocked on a condition object. T1 accesses the critical section, does its thing, and then it goes ahead and it waits, and that allows T2 to start running, right? So you can take turns going back and forth. You're kind of passing the baton on and off. So you can get flexibility. That's something that's really difficult to do with a reentrant lock, for sure. You can do it to some extent with a semaphore, but it's much more simplistic with semaphores, whereas semaphores just let you check the value of a count, 0 or 1, for example. With a condition object, you can check arbitrary conditions, in other words, arbitrary code. A user object can also define multiple condition objects. That's another thing that makes it more flexible. So each condition object can have a separate wait set. So as we saw before, with the not empty and not full conditions, you can have things queued up waiting for the queue to be not empty. You could have things queued up to be waiting for the queue to be not full, and so on and so forth. And so those can be queued up differently. You have to use condition objects very carefully, though, in order to avoid problems. And there's a bunch of very famous problems I'll mention briefly and show you some examples of. First and foremost, you should almost always wait on a condition object in a loop. So it should almost always look like this. There are exceptions to this, but it's almost always the case that you use a loop. And the reason why you need to do that is because you often have to retest the condition expression, such as count equals 0, since you don't necessarily know what the state of the condition expression is just because somebody woke you up. And that has to do with the non-determinism of concurrency. So remember the example we gave before with waiting for the pizza and waiting for the keys. You don't necessarily know when you wake up, when someone rings the bell, who has the pizza, who has the keys. So you've got to check, and if the world isn't what you're expecting or what you need, and you don't get the resources you want, you've got to go back to sleep. And if you read this link at the bottom, it gives you a little bit more explanation of that. The other reason for doing this is to guard against spurious wake-ups. So spurious just means something that's not really true, which is why we have Pinocchio here. So a spurious wake-up, which you can read about here, occurs very infrequently, but you have to be prepared for it. And what can happen with spurious wake-ups, and it's a little bit of a mystery as to why they occur. If you read the link here, it tells you why, but these are not common things, but you still got to guard against them. Your thread can be awakened even though nobody notified it. And again, why that happens is sort of one of the mysteries of the universe. It's like stray gamma rays striking your computer and causing the bits to flip and so on. But you've got to be prepared for it. So guarding against spurious wake-ups is important, and that's called the spurious wake-up bug. And so what it means is that a thread could be awakened or awoken from its wait state even though no thread signaled the condition object. So you've got to guard against the spurious wake-up problem. You also need to make sure you use condition objects with locks. There are some circumstances where you don't need to use a while loop, but you always need to use a condition object in conjunction with a lock. And the reason for that is to avoid something called the lost wake-up problem. So we've got the spurious, we have the spurious wake-up problem, we have the lost wake-up problem. They're different problems. And the lost wake-up problem occurs if you don't acquire the lock when you are checking the condition. And so you can read more about that here at this link. And basically, if the following three things happen, a thread calls signal or signal all, another thread is between the test of the condition and the call to await, and the lock isn't held. So if the lock is not held and these things happen and no other threads are waiting, then you'll end up with what's called the lost wake-up problem. And that typically ends up with your system sort of grinding to a halt and deadlocking. Or not deadlocking, just stops. And so you need to avoid that. And the easiest way to do that is to make sure you always have acquired the lock. So you have to make sure that you lock the lock that's associated with the condition object before you check the condition and before you call to wait. So that's the lost wake-up problem. Internally, as you recall, await will release and reacquire its lock, but it has to be locked in the first place. So if you don't lock it, then it's going to be releasing something that's not already locked, which is also a bug too. Another subtlety is choosing between signal and signal all. Now I mentioned before for the built-in monitor objects that come out of the box with Java, the choice is often use signal or use notify all the time, which is a sad thing because you have thundering herd problems. But when you have a condition object, you get a choice. But with everything in life, when you have a choice, you have to know how to make an informed choice. And as a general rule of thumb, you should try to use signal rather than signal all because it's more efficient and it avoids the thundering herd problem. So that, of course, raises the question, when can I use signal versus signal all? And I'm going to describe the conditions under which you can do that. And in order to do this, we're going to use the ArrayBlockingQueue as the way to understand what's happening here. So we have the ArrayBlockingQueue, and it's going to demonstrate these things we're about to talk about. The first condition that must hold if you want to use signal rather than signal all is you need to have so-called uniform waiters. What the heck is a uniform waiter? Does it mean that they wear a uniform? No, it means that you are going to have each thread execute the same logic when it returns from await for that condition. So you can see here that the take method demonstrates this property because when it returns from await, it checks to see if count is 0, and if it is no longer 0, it then calls extract. So the same thing happens for any thread that's waiting for the not empty condition to be signaled. So it's uniform. And the other property that has to be satisfied is one in and one out. So remember, signal will enable one and at most one thread to proceed. And it turns out for our array blocking queue, that's precisely what we want, because when put is called, it calls insert once it is able to, once the queue is no longer full. And that calls signal on not empty. So the intent here is to let one and one thread wake up. If there's anybody waiting, one waiter will wake up and get a chance to pull something off the queue. So you've got to have uniform waiters, and you've got to have one in, one out. So the array blocking queue satisfies both those conditions, so it's fine to use signal on the condition object for the not empty condition rather than having to use signal all. There are other situations where that doesn't apply. In particular, if you were using the built-in monitor objects, then you would have non-uniform waiters, because there's only one condition variable there in the monitor object, and you would have non-uniform waiters because one type of waiter would be waiting for the queue to be empty, or not empty, and the other type of waiter would be waiting for the queue to be not full. So you'd have the same basic, you'd have different code under two different conditions, which is why you need to use notify all as opposed to notify there. Very, very subtle stuff. And it really pays, if you use condition objects, it really pays to understand it, but it takes a little while to sift through it. Keep in mind that condition object inherits wait, notify, and notify all from Java object. So if you take a look, here's Java object. It's got notify, notify all, and wait. And then you have condition object, and it inherits all those things, and then it fills in await, signal, and signal all. Do not mix and match these methods. Chaos and insanity will break out. I've done it. I've seen lots of students do it. Depending on which assignment we do next, you might get a chance to learn this the hard way. But invariably, somebody gets confused, and they call wait on a condition object, and their code grinds to a halt. They can't figure out why. That's why. So I'll remind you now, but if we do that assignment, you'll definitely learn, probably the hard way, what to do if you get it wrong. Condition object is used quite extensively within some of the Java concurrency packages. Java.util_concurrent uses it all over the place for things like array blocking queue and so on, and array linked, array block, let's see, linked blocking queue. Linked blocking queue, array blocking queue both use condition objects, and it's available in concurrent locks and so on. As a general rule of thumb, though, you typically hide it behind higher level abstractions, because programming directly to condition objects is very tedious and error prone, so we encapsulate it within these other classes. And then they provide us with a nice message passing abstraction that has higher level semantics like take and put that block, depending on the conditions, but the conditions are hidden from you mercifully. Okay, so that is the end of the last part of condition object.